I'm going to get started. I want to first thank everyone for coming today. I'm going to be talking about deep sea lights, the evolution of bioluminescence, and light detection in the twilight zone. So bioluminescence is relatively rare on land, but it's a common phenomenon in the marine environment. You're going to just see some examples of some deep sea bioluminescence in the form of coral bioluminescence. Here's an example of an anemone bioluminescence and a sea pen. And these organisms, especially those that live in the deep sea, are really dependent on the generation for light, not only in their survival, but it's related to communication, feeding, and defense. So really understanding this behavior, this trait, in an evolutionary context will allow us to better relate it to their survival for the survival of these species. So I'm going to be talking about maybe a system that you're less familiar with, and this is the evolution of bioluminescence in my favorite group. This is a group of deep sea shrimp. This family is the Oplophoridae. They belong to the infraorder Charidia, which was in the order Decapoda. Total, there's about 70 different species. They belong to 10 extant genera. Most of these shrimp are found in the mesopelagic, but their ranges can go all the way into the bathypelagic and can extend beyond 5,000 meters. Typically, or generally, they have a cosmopolitan distribution, and some of these species participate in the largest migration on Earth. That is this nocturnal vertical migration, where these species actually travel hundreds of meters every single night to migrate into shallower waters to feed and avoid predation. So as I mentioned, these shrimp have several different modes of bioluminescence. The first is in the form of this bioluminescent secretion, where the shrimp pretty much vomits out this luminescent cloud. It's known to be used as a defense against predation, and this is just kind of a silly animation of what it looks like. This is a little bit more of what it looks like. Let's pause that. I didn't realize sound was going to be on. But you can start to see the bioluminescent secretion in the video, but this is a species Oplophores Gracillorostris, where we took this, or my collaborator Dante Canolo took this picture under red light. Okay, the second mode of bioluminescent that some of these species have are in the form of these bioluminescent light organs. These are called photophores. These are complex light-emitting organs. They're made up of these bioluminescent cells called photocytes. Photophores they also have reflectors. Some of these can be lens or lensless, and they have filter structures. So these photophores have been shown experimentally in some species to be used in counter-illumination. Now, counter-illumination is just a form of camouflage. So when these photophores are turned on, if you can imagine yourself, they're supposed to emulate that of downwelling sunlight. So if you're a predator swimming below one of these shrimp, these photophores are turned on and you're looking up at the shrimp, it's supposed to help with camouflage, and that's what that picture shows, is the fish with the photophores turned on versus turned off. Now, within these shrimp, it's known that every single species within the family does have this bioluminescent secretion. However, there's only three genera in which the species have photophores. So this really kind of begs the question is, how did these different modes of bioluminescence evolve within these deep sea shrimp? And so the very first question we wanted to ask was, how did photophores evolve across this opal tree? So what you're looking at here, this is a maximum likelihood phylogeny. It contains 8 genes, mitochondrial and nuclear, of the family Opal-4idae. We did ancestral state reconstruction, and as expected, this secretion was the ancestral state for the family. And we did find a clade, a monophyletic clade, which included all of those photophore-bearing shrimp. And we found a second clade that contained all of those shrimp that did not possess those photophores, or those light-emitting organs. So this kind of gets us thinking, well, why did photophores evolve in some species in the family and not others? One hypothesis is that a lot of these species that have photophores show very strong vertical migration. So these ones that have the photophores migrate more shallower than those that don't. So they could be evolving having these photophores because they need them for counter-illumination in these shallow waters. Another, maybe more contentious argument is that they possibly might play a role in communication or conspecific recognition. But these are some kind of hypotheses that we're trying to investigate a little bit further. So, in order to investigate the evolution of bioluminescence, and specifically this structure, the photophore, I wanted to look at not only photophores in a little bit of a deeper context, but also the visual systems of these shrimp. So, it's assumed that visual sensitivity, and especially those organisms that live in the deep sea, that their visual sensitivity is really limited to these blue light wavelengths. So in the deep sea, you really only have 2 forms of light. You have that of downwelling sunlight, which pretty much is obsolete below 1,000 meters, but you also have light in the form of bioluminescence. And these lambda max ranges from anywhere from 460 to 490 nanometers. So you would expect shrimp to have that visual sensitivity within these blue light wavelengths. However, there's quite a few studies that are based on physiology that have tested the spectral sensitivity of these photophore-bearing shrimp. And what they found is that these photophore-bearing shrimp have something called a dual sensitivity system. Well, that's what we're calling it, at least. So they have this sensitivity to blue wavelengths, but they also have this sensitivity is shifted also into a near UV. So this has been shown in several cases based on physiology, but we're also going to look, but it's never been looked at using genetic or genomic tools. So we wanted to investigate this visual system using genomics. So we're using RNA-seq to investigate the visual system. We sampled 5 species, selected those that had photophores and those that didn't. Generated about 20 to 30 million reads per individual. And underlying spectral sensitivities of organisms are the absorbance properties of photopigments. And specifically, photopigment is made up of an opsin bound to a chromophore. Opsins are really the proteins that are responsible for light detection. So I'm going to focus on just talking mostly about opsins in this talk, but we are looking at other genes that are involved in phototransduction. So we're interested here in opsins, those that are responsible for light detection. And we annotated these transcriptomes to search for genes involved in light detection. To do this, we used a method called PIA, or phylogenetically informed annotation. This is exactly what the name implies. We basically place uncharacterized genes on pre-made phylogenies in order to annotate them and identify them. This pipeline that is currently in place identifies, there's a suite of 109 different gene families. All of these gene families are known to play a role in light detection. So what I'm going to show you now is just the opsin phylogeny. Let me orient you. This is a circle tree of an opsin phylogeny. We divided the opsin phylogeny into 2 different categories. Red indicates the long wavelength sensitive opsins, blue is short wavelength sensitive opsins. There's about 200 different arthropods that are included in this tree. Everything in blue indicates those shrimp that have photophores. Everything in green are the shrimp that don't. So the first thing we see is that we've detected long wavelength sensitive opsins and short wavelength sensitive opsins in all of the opophores that we've sequenced so far. But we have detected a higher diversity of opsins in these photophore bearing shrimp. So this is an interesting result that we're finding. Could this show possible evidence for increased sensitivity? Maybe. We're adding a lot more data right now, and it's turning out to be a little bit more complex than we originally anticipated. So why the increased sensitivity in these photophore bearing shrimp? There has been studies that show that photophore luminescence actually secretes a different wavelength than the bioluminescent secretion. Is this increased sensitivity a mechanism for them to distinguish between the different forms of bioluminescent? Is it just increased sensitivity because these do migrate into shallower waters? I'm not really sure. But as I mentioned, we are really investigating this system. We are adding a lot more species. We have representatives for almost all of the genera within the opophores. Okay, switching gears and looking at photophores now. So we wanted to look at photophores. Specifically, we're trying to look at, can these photophores, do they do something other than just emit light? And really there's two main systems of how photophores can be classified. We have a bacterial system and we have autogenic systems. Bacterial systems are where you have a light organ where you have symbiotic bacteria, and it's the bacteria that's responsible for the light emission. In autogenic systems, such as the shrimp that I'm studying, they can produce all of their own substrate and enzymes needed for the production of light. And this study was really kind of inspired by a study back in 2009 where Tong et al. Found that these photophores in this bacterial system could actually perceive light. So I wanted to see if in our autogenic system, if our photophores can actually do the same thing. Methods, exactly similar to those that I showed you for the eye section. However, instead of extracting RNA from eyes, we're extracting it from photophores. And this is what we're finding. So you're looking also at the exact same tree. The only difference here is now the colors mean something different. Everything in yellow are opsins that we identified from eyes, and everything in purple are opsins that we identified from the photophores. So we did find opsins in the photophores, all right, so that's good news, but so what, right? There's been a lot of studies that find opsins all over the place. So the real question, and those opsins were identical to, the photophore opsins were identical to eye opsins. But we want to know if they are functional or not. So this next thing we're doing is the phototransduction cascade is really how an organism, so it converts the the light to an electrical signal. There's a lot of different genes that are involved in the phototransduction cascade besides opsins. So we are looking for those genes in the photophore, and we have found nearly all of the genes that are responsible in the phototransduction cascade. This just shows a pie diagram that we term this an oculogram, where the proportion of isoforms represents each component of that phototransduction pathway. Colleagues at Nova Southeastern University are using SEM, scanning electron microscopy, to look at these photophores in great detail. We're seeing evidence for when photophores are actually exposed to light, we see damage. Okay, but we have a lot more to do on this, and also look at what the photophores look like when they're not exposed to light. We're using secondary structure to infer function. Colleagues in Hawaii are using in situ hybridization to see where these proteins might actually be expressed in the cell. Okay, and I'm done. So this is exciting for us. We're really just getting started. It's the first indication that these lights might play a role in light detection. It's also possible they could play a role in counter-illumination. And it has broad-spanning implications because autogenic organs can be found across every animal phyla on Earth. And that's all I have. Thank you very much.